Okay, so we derived the general probability formula for binomial distribution. It took like 3 videos to derive that. I hope you could see the idea. So then back to the general setup. We write y, random variable y follows a binomial distribution, and then we denote the parameters by n and p. N is the number of experiments, and p is the probability of success. And then y is the number of success out of n trials, and it can take n plus 1 possible values because n minimum it is 0 and n most it could be n, right? When all the experiments are success, then you get n, and when all experiments are failure, you get 0. So there are n plus 1 number of possible outcomes. And probability for each outcome y, like lowercase y is a specific number of success, then you can calculate the probability this way. So then think about this. This probability formula depends only on parameters n and p and lowercase y. But lowercase y is what you choose. If you're interested in probability of 2 success, then y becomes 2. If you're interested in probability of 3 successes, then y becomes 3. So y is lowercase y is also a known value, a value of your choice. So basically the only unknowns are n and p. That means with these two parameters, you are summarizing the probability on n plus 1 points, right? So if n was 100, then there are 101 possible outcomes. So there are 101 probabilities for each outcome, for all the outcomes. But basically, you don't need to know all the 101 probabilities, but only 2 numbers, n and p. Then you summarize the probability distribution, and you don't lose any information. That is the point of studying this scientific, like statistical model. Binomial distribution. Distribution can be simplified without loss of information under a certain set of assumptions. Okay. Okay. Then keep this in mind. The parameters are n and p. So then, how they look? How do they look? The histogram looks like this. When I fix the sample, the experiment number to 20, and when I change the success probability from 10%, 50% to 90%, as you can see, the number of success will increase. So the number of success is usually 1 or 2 or 3 when success probability is 10%, right? And when it is 50%, of course, it is centered and symmetric. Number of success and number of failure must be symmetric, so it is around 10 with symmetry. And when the number of when probability of success increases to 90%, the most probability is around, like say, 19, 18, 17, right? So the number of success is distributed on the larger side, which is natural. So by changing the parameter, the shape of the distribution changes, but according to the formula. Okay. Now, when you change n, as you increase n, the difference is your distribution will be more spread out, right? More dispersed. And when, like for example, I fix the probability of success to 50%, and the number of trials, when number of trials was 5, its range is between 0 and 5. So range is only 5, so it's distributed here. But when you increase n to 10, then you get a range between 0 and 10. So distributed, well, still it's symmetry, but it's spread out. And when you increase it to 20, then it's even more spread out. By the way, even though it looks like there is no probability here, but there are. Actually, the probability is not 0. It is close to 0, but not exactly 0. So when you try 20 experiments, if you are super lucky, then you may get all success, or if you are super unlucky, then you may get all failures. Similarly, there are non-zero probabilities here, even though we can tell on this graph, like there are probabilities everywhere, just the probability is very, very small. So we don't see them right here. Okay. And the next property is about the mean and the variance. Oh, remember, in a binary distribution, actually which is a simplest possible binomial distribution. In a binary case, the mean was p and the variance was p times 1 minus p. So binary distribution is a special case of binomial when n equals to 1. When you do the experiment only once, that is a binary distribution. Now, when in general, the binomial distribution has mean n times p, which is intuitive. You do n number of experiments and p of them, on average, p% of them are success. So then expected number of success should be n times p, right? So for example, when you throw a coin 100 times, then expected number of heads must be 50 because out of 100, 50% is 50, okay? And variance is n times p times 1 minus p. So, excuse me, p is probability of success, 1 minus p is the probability of failure. So the second part, latter part, last two terms are the same as a binary distribution. And when you increase the number of trials, the range of y increases. So as you just saw from the graph, like this, the variability increases. The histogram becomes more flatter and like spread out to a wider interval. So n is also multiplied. In here, the same intuition holds in these cases. So when when n increases and p increases, the mean changes, mean increases, the number of success increases, of course. But for variance, variance increases in n, but not exactly in p. Variance is maximized when p equals 50%. But when p approaches to 0% or 100%, the variance will decrease. As you see here, the spread, like when p is 10%, it is concentrated on the lower side and in 90% on the other side. But when it is 50%, it's more spread. The peak is lower, so less concentration when p is 50%. So all these shapes can be explained by those mean and the variance. Okay, so then it is easy to apply that idea. So in your whole quiz, suppose that you have in a quiz you have 10 questions and each question has 5 options, and you just randomly choose one of them, right? And then in that case, and if you choose a correct answer, you get 1 point. If it is a wrong answer, you get 0. And then what is the mean and variance of your quiz grade? So you can apply this formula, right? I just want you to see how simple it is. The answer is clear. Out of 10 questions, you are likely to choose 20% correct. Right? So the expectation is 2 points, but the variance is 1.6. 10 times probability of success, 0.2, times probability of failure, 0.8. So variance is 1.6. So using this, you can calculate how better you are. better than randomization. So if you get lower than 2 points, then you are worse than the randomization. Okay. Okay, from now on, I'm going to show you two more examples where we can apply binomial distribution, and we'll just show you how to calculate some probabilities. So first example is about overbooking. So here, think about this case. Airlines airlines sell more tickets than available seats. So because they know some tickets will be canceled, so selling more, expecting cancellations, will improve their profits. Okay, so suppose that, simplify all the cases. An airline has 20 passenger seats, and the airline accepts 22 reservations. So there are only 20 seats, but they sell more tickets than the seats. And they know that the probability of cancellation is 10%, and cancellations are independent, as we assumed. You know it is a binomial distribution. You know the number of cancellations, or number of, so I will define Y as the number of reservations that are not canceled. So this is what actually matters. This is the number of passengers who come to the airport to take the flight, right? So if it's if there are more passengers coming to the airport than the number of seats, then the airline is in trouble, need to compensate to the passengers. Then and we know this is binomial distribution. What are the parameters? That is the first step. Think about this. The simple question, you need to find what is the correct parameters. Once you know those parameters, you know how to calculate the mean, the variance, the probability. So this is almost everything and most important thing to find. But what's tricky is, there are two possible numbers, 20 and 22. What is the parameter? The answer is, first, P is the probability of success. I set up a trap here. In our previous examples, we counted number of cancellations. We defined Y as the number of cancellations, but now we are counting the other side, non-cancellations, right? In our previous examples, we counted cancellations as success, but now we count non-cancellations as success. So the probability of success is not 10% but 90%, because it depends on what we define as a success. That's the difference. So remember what we count, and it is 90%. And then the other side, N. Is it 20 or 22? 22 is the answer, because one reservation is one experiment. So there are 22 experiments. So you can have 22 different possible outcomes. Or an easier way to find this experiment is, this parameter is that you can think about the maximum possible outcome. Here, we are defining binomial variable in this way, the number of reservations that are not canceled. The maximum possible value is when all passengers with reservations come to the airport. That is 22. So the parameter can be understood as the maximum possible outcome. So the answer is D. So this is two traps I set up, so to tell you that it is not as straightforward as you think. It is very important, but you have to be more careful when you just check the parameters and find the parameters. Okay. And then in this case, in this example, maybe the probability we are interested in is the probability of overbooking when there are more passengers than seats. So let's see. I'll just show you how to calculate probability that the number of non-cancelled reservations is strictly greater than number of possible seats, available seats. The problem here is our formula does not apply to inequality. Our probability was defined by an inequality, but our formula is not. Like, look at this. We define formula based on equality, so we have to divide this inequality into equalities. So probability that y is strictly greater than 20 is either y equals 22 or y equals 21. Because the maximum is 22, there are only two possible cases, and you apply formula for each of them. When you have 22 passengers coming to the airport, 22 passengers want to take the flight, then you choose 22 out of 22, which is only one possible case. There is no cancellation. That's the only combination. Times success. In this case, success is non-cancellation. 90% happens 22 times. But failure, like cancellation, does not happen. So you don't need to multiply this part. Exponent of 0 equals 1. Okay, so this is useless. Anyhow, this part equivalent to this probability. And applying the formula to the other outcome, you are going to choose 21 out of 22. 22 chooses 21, and success happens 21 times, failure happens 1 time. So this is 1, and this is this. And when you choose 21 out of 22, there are 22 possible cases, because this means there was only one cancellation. So it can be 1 of 22. So there are 22 possible scenarios, and each of the scenario has this much probability. So in the end, the probability of overbooking causes a problem is 33% in our example. So probability is pretty large. Almost one third of the flights will have trouble flying passengers. Now then, I want you to try this question. Now change the number of reservations to 21. Previously, the airline sold 22 tickets, but they realized that was too much. So they reduced the overbooking to 21. Then, what would be the probability of this overbooking causes a trouble? Apply the formula. You can go back to the slide and try it by yourself using the formula. Pause the video now. Let me show you. So probability greater than 20. Now because there are only 21 reservations, the only possible outcome in this event is y equals 21, right? So it's simple. So 21 chooses 21, which is simply 1, and 90% happen 21 times. So now you are selling only one more ticket than you can accommodate. So the problem happens when all reservations are not canceled. So 90% happens 21 times. There is only one scenario for that, which is 10%. Okay, about 10.9%. So then think about this. Okay, it's the calculation is straightforward using the formula. But what I want to show you here is that the change from 20 to 21 could be small, or you may think it's a big change. But anyhow, the change in the probability is also counterintuitive. You cannot calculate this change without using the formula. It is not easy to imagine how much it would make the difference. Okay, so binomial distribution is intuitive if you understand how it works, but it can be quite weird. It may seem weird without understanding what is going on. When I tell you the probability will change from here to here, without knowing how it works, you will wonder why this kind of change happened. So that is complicated. Okay. Another example, quick, similar example. Think about this. Say I have a battery manufacturing firm, and my batteries are defective with 5% probability. And assume that the batteries are independent. And I ship my batteries, I sell my batteries to a client, say a smartphone manufacturing firm, and they inspect my batteries. And if there are too many defective batteries, they are going to reject my batteries, and I have to reproduce and reship the batteries to them. So then how it works is, suppose that simply, so when I deliver my batteries to the smartphone maker, they randomly choose 10 batteries out of my shipment, and they are going to accept only if 2 or fewer batteries are defective. So when you randomly choose 10, and if they find 3 batteries are defective, they are going to return my delivery. Okay? So it's kind of inspection. And in this case, I'm going to define Y as the number of non-defective batteries in this inspection process, right? So then what is the probability that my battery delivery is returned, rejected? Calculate, based on this scenario, find the correct statistical notation that we are looking for. Okay, so first you need to understand we are counting non-defective batteries. But the rule is what I said. I described the rule in terms of number of defective batteries. So if there are 2 or fewer batteries are defective, it is accepted. That means if the non-defective if there are 8 or more non-defective batteries, then you are going to be okay. However, I am asking you the probability of rejection. So, like I said, 8 or more batteries are okay, but then the other side is rejected if 7 or fewer batteries are non-defective. So the answer is E. So you have to think about that. 2 or fewer accepted if 8 or more batteries are non-defective. That means rejected if 7 or fewer batteries are non-defective. So the answer is E. So you have to think about what you are counting and whether you are accepted or rejected. Think about the inequality in your mind. So anyhow, we would like to calculate this probability, and in this scenario, the binomial distribution for Y is with parameter 10 and 0.95. So 10 is obvious because they randomly choose 10 batteries, but 95%, because we are counting the number of non-defective batteries, so not defective is success, right? That happens with probability 95%. So there are 5% defective batteries, which is failure. So failure probability is 5%, but success probability is 95%. So probability, the parameter P must be 0.95, not 0.05. So that is, once you understand that, then it is not easy to calculate that. So you have to think about inequality you have to break down the inequality probability into probability with equalities. But there are 8 possible outcomes. So what I recommend here is, instead of calculating probability of rejection, I recommend you to calculate the probability of acceptance. So instead of calculating probability 7 or lower, you can calculate probability 8 or higher, and then subtract that probability from 100%. And this is easier because you just need to calculate 3 probabilities, 10, 9, or 8. So probability greater than or equal to 8 includes these 3 cases. So the binomial probability formula, if you use them, you get these numbers. So in the end, it's only 1.15%. Okay. Okay, in this chapter, we learned binomial distribution. It is, I find it very interesting to explain the underlying mechanism of binomial distribution. I hope you also liked it. In the next video, we are going to start the normal distribution, which is the most important distribution in say not just in statistics but in any science. So like you, I hope you come back soon and watch the next video more carefully. Okay. Thank you for watching. See you later. Bye.